So, in this lecture we will start with half range Fourier series. So, earlier on Fourier series whatever we are covered is that the general Fourier series of a generalized function, Fourier series for odd and even functions, and Fourier series of a function which is defined in some arbitrary period. The next one is half range Fourier series. Half range Fourier series, what happens? It is generally required to obtain a Fourier series expansion of a function for the range 0 to L, which is half the period of the Fourier series. If you know, Fourier series is defined, Fourier series of a function is defined in either minus L to L, minus pi to pi, like this. But in certain real life problems, we have observed that a function is defined in 0 to L say only, and we want to find out the function, we want to express the function in terms of cosine and sine terms, that is in terms of Fourier series. So, we want to study if a function is defined in 0 to L or in the half range Fourier series. In that case, how to find out the Fourier series of a function which is defined in 0 to L. So, what we can do? We can extend the function to cover the range from minus L to L, so that the new function will be either even function or it may be odd function. You see, it is originally defined from 0 to L. Now, I am defining it again 0 to minus L, and I can redefine the function in 0 to minus L in such a way that the function may behave like an odd function or it may behave like an even function. So, the Fourier expansion of such a function basically will be consisting of either sine terms or cosine terms only, because already we have observed that if a function is odd function or even function, in that case it will be consisting of sine terms or cosine terms only. So, in such a case, the graph for the value of x in 0 to L will be same, whether I am defining it as odd function or even function, but outside 0 to L it will be different, and it will depend on whether I have defined it as odd function or I have defined it as an even function. So, the basic idea is whenever the function is defined in 0 to L, in that case I will redefine the function in 0 to minus L also, so that the function is now defined in minus L to L, and while doing so I will do it in such a fashion that f x will be either even function or f x will be an odd function. And once the function f x is defined in minus L to L, I can always express f x as a Fourier series. Now, the nature of the function will remain same in 0 to L, but in 0 to minus L the graph of the function will be varying depending upon whether it has been treated as odd function or it has been treated as even function. So, that we will see the half range sine series, the first one. Suppose f x is defined in 0 to L. So, we want to find out half range sine series and where the function f x is defined in 0 to L. So, we are defining a new function capital F x, a new function capital F x, such a fashion that capital F x is f x when it is 0 to L and minus of minus f x when it is minus L to 0. So, I am defining a new function f x equals small f x when x lies between minus 0 to L, and it is minus of f x when it is lying in between minus L to 0. So, that your capital F x is an odd function is an odd function in the interval minus L to L. So, now I know f x is consisting of only sine terms. In this case, f x will consist of sine terms only. Please note this one. So, I am redefining the function capital F x such that capital F x in minus L to L, it becomes an odd function, and capital F x consists of the sine terms only. Further, what happens? In 0 to L, in the this interval, capital F x equals small f x. So, capital F x gives what? The required sine series solution, sine series of f x in 0 to L. In 0 to L, f x, capital F x will be represented by the sine series, and we can write down f x equals summation n equals 1 to infinity b n into sine of n pi x by L, where your b n will be 2 by L 0 to L f x into sine of n pi x by L into d x. So, therefore, half range sine series of a function f x is equals to summation n equals 1 to infinity b n sine n pi by x, n pi x by L, where your b n is 2 by L 0 to L f x into sine n pi x by L. And already you have seen how we are arriving to these formulas. Now, come to half range cosine series. Just like half range sine series, in half range cosine series I can define again a new function capital F x, which is equals to small f x, where x lies between 0 to L, and this will be equals to f of minus x in minus L to 0. So, that your f x is an even function, f x is even function in minus L to L. So, we are redefining the function capital F x, which is equals to f x in 0 to L, and minus f and f of minus x in minus L to 0. So, by this definition, capital F x becomes an even function in minus L to L, and we can find out the Fourier series of the function f x in this interval minus L to L, and since f x is an even function, therefore, it will be consisting of the cosine terms only. So, that I can write down in the half range in minus L to L, your f x is equals to small f x, and therefore, the cosine series of f x is the required cosine series of small f x also in the interval 0 to L. In minus L to L, the characteristics will be different. Therefore, I can define f x equals a 0 by 2 plus summation n equals 1 to infinity a n into cos of n pi x by L, where your a naught will be 2 by L into 0 to L f x dx, and your a n will be equals to 2 by L 0 to L f x into cos of n pi x by L into dx. So, if the function f x is defined in 0 to L, then the half range cosine series of f x will be equals to a 0 by 2 plus summation n equals 1 to infinity a n cos n pi x by L, where a naught will be 2 by L 0 to L f x dx, and a n will be 2 by L 0 to L f x cos of n pi x by L into dx. So, let us see this thing. In half range series, sine series we are defining capital F x as small f x in 0 to L, whereas in minus L to 0 we are defining it as minus f of minus x. So that capital F x is an odd function in the interval minus L to L, and f x can be expanded in terms of Fourier series, which will be consisting of sine terms only. And in the since f x equals small f x in 0 to L, therefore, sine series of f x will be the required sine series of f x in 0 to L. And in that case, f x we can define as summation n equals 1 to infinity b n sin n pi x by L, where your b n will be 2 by L 0 to L f x sin n pi x by L into d x, which we have done earlier. Similarly, you can define half range cosine series. Here the new function capital X will be defining as f x in 0 to L and f of minus x in minus L to L. So that f x is an even function in the interval minus L to L, and the Fourier series of f x we can find out, and it will be consisting of only cosine terms. Again, in the interval 0 to L, capital F x equals small f x. Therefore, cosine series of f x will be the required cosine series of small f x in 0 to L. So that we can write down f x equals a 0 by 2 plus summation n equals 1 to infinity a n cos n pi x by L, where your a naught is 2 by L 0 to L f x dx, and your a n will be equals to 2 by L 0 to L f of cos n pi x by L into dx. In case of half range sine series, we extend the function reflecting it in the origin, please note this one. And in case of range of cosine series, half range cosine series, we extend the function reflecting it on the y axis. So, please note these things. In one case, we are reflecting it in the origin, and in the cosine case, we are reflecting it on the y axis. So, let us see how it works with examples. We want to find out the half range sine series for the function f x equals x when x lies between 0 to 2. For the same function, effectively, afterwards we will see what is the half range cosine series, and we will try to find out this one. Now, here if you see the graph of f x in 0 to 2 is the line this one 0 to a this one. Now, we want this thing that let us extend this function f x in the interval 0 to b, that is from 0 to 0 b we are extending it, or in other sense 0 to minus 2 we are extending it, so that the function is symmetric about origin. Please note this one. We are making it in such a way, since we are finding out the half range sine series. So, we will make it symmetric with respect to origin, and therefore, this function will represent an odd function in minus 2 to 2. So, please note this one. Although the function is given as f x equals x in 0 to 2, and the graph of this is O A in this graph. Now, we are extending it in 0 to minus 2 also in the form of O B, in such a fashion that it becomes symmetric with respect to the origin, so that it will represent an odd function in the minus 2 to 2. So, basic idea is whenever a function is given and we have to find out the half range series, whether it is cosine series or it is sine series, we will first draw the original graph in the given interval, that is 0 to L, then extend it in 0 to minus L with respect to, I will extend it in such a fashion that it will be symmetric either with respect to origin or with respect to the y axis, depending upon whether I want the half range sine series or half range cosine series. Once I have done this, then I can solve this problem using the normal process as we have done earlier. So, now let us see what is the next step. So, we have defined the function f x in minus 2 to 2. and since the function is an odd function, so it will contain only the terms of sine only. So, we can write down f x equals summation n equals 1 to infinity b n into sine n pi x by L, value of L is here 2. So, it will be n pi x by 2, please note this one, this term. Similarly, whenever I am writing b n will be 2 by L, L is 2 and the limit will become 0 to 2 f x into sine of n pi x by 2 into dx. Now, in 0 to 2 the value is of f x is x. So, you can write it as 0 to 2 2 sine not 2 0 to 2 x into f x is x into sine n pi x by 2 into dx. If I integrate it, I am just writing at a glance minus 2 x by n pi into cos of n pi x by 2 plus 4 by n square pi square into sine of n pi x by 2, where x will vary from, limit will be from 0 to 2. So, that if I put the limits of b n over here, I will obtain b n equals 4 into minus 1 to the power n by n pi, then 1 minus sine will come. So, that b n equals minus 4 into minus 1 to the power n by n pi. So, that I can write down b 1 equals 4 by pi, b 2 equals minus 4 by 2 pi, your b 3 will be 4 by 3 pi, like this way it will go. So, Fourier series of f x in the interval 0 to 2 then becomes f x equals 4 by pi into sine of pi x by 2 minus half sine of 2 pi x by 2 plus 1/3 sine of 3 pi x by 2, and like this way it will go on. So, I think it is clear that whenever the function is given to us and we have to find out the half range, say sine series, in that case we are extending the function in such a fashion that it will be symmetric around origin and we are extending it from 0 to minus 2. So, that we are redefining the function f x in minus 2 to 2 and which becomes an odd function. Then using normal process f x equals only sine term will be there, that is b n sine n pi x by 2 will be coming, and we can find out the values of b n. From there we can write down the series of the function f x given function. So, once we have done it, then f x is in the full period minus 2 to 2 will contain sine term as I told, and f x we are writing this b n is 2 by 2 because L is here 2. So, if you calculate the value you will obtain b n equals minus 4 into minus 1 to the power n into n pi. So, that you can calculate b 1, b 2, b 3 all these, and from here you can write down the Fourier sine series, half range sine series of f x in 0 to 2 will be f x equals 4 by pi into sine pi x by 2 minus half into sine of 2 pi x by 2 plus 1/3 sine 3 pi x by 2, and like this way it will go on. Now, let us take the same example f x equals x as a, we want to now express f x equals x as a half range cosine series in 0 to 2. So, in the earlier case what happened, if you see in the earlier case whenever I am writing f x equals x, always it is something like this. If it is 2 and here if it is say minus 2. So, I extended the function like this way up to this in 0 to minus 2. Now, for the function f x, whenever you want to find out the half range cosine series. So, basically cosine series means, as I told you, for the sine series it has to be symmetric with respect to the origin, whereas for the cosine series I have to extend the function in such a fashion in the interval 0 to minus 2 in such a way that it will be symmetric with respect to y axis, if this is your y axis, or in other sense your figure will be something like this. So, please note this one. In this case, I am extending it in such a fashion that in one case it is symmetric with respect to origin, whereas in this case it is symmetric with respect to y axis. So, that the function becomes the even function in this particular interval minus 2 to 2. So, if you see this one, in the interval minus 2 to 2, the figure is like this. My original function was 0 to 2, which is same. Now, I am extending it in such a fashion that it is symmetric with respect to y axis. And please note one thing, whether I am expressing f x equals x as a half range sine series or half range cosine series, the nature of the function in 0 to 2 will remain same, because the graph of the function is same in 0 to 2, and in 0 to 2 minus 2 only I am changing the nature of the function. In one case I am describing it as an even function, in other case I am describing it as an odd function. So, please note that whether I am defining same function as a half range sine series or half range cosine series, its characteristics, its property, its graph will remain same whenever I am talking about the period 0 to 2 only. So, let us see now in this range what happens. So, therefore, the Fourier series will be containing of cosine terms only. So, that f x I can write down a 0 by 2 plus summation n equals 1 to infinity a n, again like earlier problem, here also L is 2. So, that I will obtain a n cos n pi x by 2, where your a naught will be equals to 2 by 2 0 to 2 f x dx. Your f x is x. So, 0 to 2 x dx, whose value you will obtain as 2, and your a n will be equals to 2 by 2 0 to 2 again f x into cos of n pi x by 2 dx, and this is nothing but 0 to 2, your f x is x. So, that x into cos of n pi x by 2 into dx. If you evaluate the integral and substitute the limits 0 to 2, ultimately you will obtain a n equals 4 by n square pi square into minus 1 to the power n minus 1. So, that I can write down a 1 equals minus 8 by pi square, a 2 will be 0, that means even terms will be 0 when n is even, obviously from here your a 3 will be 8 by 3 square into pi square, your a 4 will be 0, and like this way it will go on. So, I obtained a naught, I obtained a 1, a 2, a 3, a 4 like this. So, that now I can write down the f x Fourier series cosine transform Fourier series of f x in the interval 0 to 2 as 1 minus 8 by pi square into cos of pi x by 2 by 1 plus cos of 3 pi x by 2 into 3 square, and like this way it will go. So, we are writing f x equals this as a series. So, from here if you see f x is an Fourier series, f x we are defining in -2 to 2, which will be consisting of cosine terms only. So, that f x is defined as a 0 by 2 plus summation a n into cos n pi x by 2, where a naught is this, a n is this integral. If I evaluate the a n, I will obtain 4 by n square pi square minus 1 to the power n minus 1. So, that your a 1 will be 8 by minus 8 by pi square, and all the even terms, that is a 2, a 4, a 6 all are 0, a 3 will be 8 by 3 pi square. So, that Fourier series of cosine series of f x in the half range 0 to 2, we can define it like this way: f x equals 1 by a minus 8 pi square by this one. So, prove that f x equals x can be expanded in terms of 0 to of course, this will take some time. So, we will start this example in the next lecture.